Okay. Yes. Hello, everyone. Welcome to the theory seminar series. We are pleased to have Maciej Obremski with us today as the speaker. So, Maciej is a senior research fellow in Devesh Agarwal's group at the National University of Singapore Center for Quantum Technologies. Before joining NUS, he has spent 3 years as a postdoc at Aarhus University, Denmark, with Ivan Demgaard and Jesper Busch-Nielsen. Before that, he was a postdoc for 2 years at the University of Warsaw, Poland. He got his PhD in 2013 from University of Warsaw under the supervision of Stefan Jambowski. His research interests mostly lie in information theoretic cryptography, randomness and randomness extractors, and non-malleable codes and secret sharing. We are pleased to have you. Welcome and over to you, Maciej.
Thanks a lot for the introduction. And yeah, I'll be talking about ALICE in the PA land, basically a privacy amplification and its connections with extractors. I'm a little bit experimenting with this format, so I'm happy to hear your feedback, how this kind of mixture of whiteboard and slides works. Anyway, let's get started. So the idea is that there's Alice, there's going to be a Bob, and they will share some high mean entropy secret. But instead of having some random but not uniform secret, they would actually want to engage in some kind of protocol, at the end of which they would be sharing some uniformly random secret.
Right, so in general, Maciej, I'm sorry to interrupt you. Did you mean for us to see the picture which says Alice and Bob and all that? I can see, wanted a uniform secret. I can see the text. I can't see the picture below. Is that supposed to be visible to us? Oh, I see something else. Okay, was that supposed to be visible to us? This Alice and Bob. I can see it only now.
Yes, this is. I can see it on the other device, unless there's like significant lag. I see what I'm showing you.
Okay, now I can see the whole thing. Yeah, okay, good. I don't know if maybe it was an issue with the lag at my end.
No, I wasn't. I was not planning on showing that yet. But okay, sure. So anyway, Alice and Bob have high mean entropy secret. They would like to have something uniform. The idea is that very often stuff is only possible when you have randomness that's uniform, and it's not possible with mean entropy randomness. But let's start with the basic thing. What's the mean entropy? So we will say that W has high mean entropy or mean entropy greater than K if and only if maximum probability, so the maximum probable atom, is happening not more often than with probability 2 to the minus K. So this mean entropy gives us some kind of bound on how nicely the distribution works, so like how nicely spread it is. So this is a standard measure of randomness in crypto. We know how to do certain things with variables that are only entropic, but a lot of stuff is not possible just with entropic randomness. So we really like to have uniform randomness. So Alice and Bob will engage in some kind of protocol. They will start communicating, and at the end of the protocol, they will have uniform randomness U. Now, well, what's stopping Alice from just picking U completely at random and sending it across to Bob? Well, what's stopping them is Eve. Eve has like control over communication channels. We will go through various variants of this problem depending on the power of Eve. From like the most toy example all the way to standard privacy amplification, and improved versions. So like even stronger variants than the standard PA. So in general, the target is there's going to be Alice and Bob. They will share W, that's high mean entropy. They want to talk. The channel will not be fully secure, but at the end, they want to derive to something uniform. Okay. So the first version, like the most vanilla version, the toy version, if you will, as there's Alice, there's Bob, and Eve in the middle is just listening to the communication. So our idea with let's just pick U that's uniform and send it across will clearly not work because Eve will know what U is. So we need to do something more clever. And for that, we will use a standard object in the field of randomness. The object is a seeded extractor. So what will be the seeded extractor? The seeded extractor is the object that takes two inputs. One input is guaranteed to have some mean entropy. The other input is short but uniform. And the output is uniform, even, let's call this S. The output is uniform, even S. Right, we can write it down as extraction of W and S. S looks like uniform and S. This is a statistical distance. Think of it as a distribution looks basically the same. All the distributions are not distinguishable. Okay, so once we have this basic object, we can finish the protocol. So Alice will start with W. Bob has the same W. Alice will pick S, that's uniformly random and short. We'll send S across. And what the both parties will do is simply extract W and S, extract W and S. And now notice that we have this cool property that output of the extractor is uniform even given S. And S is exactly what Eve knows. So Eve knows S, but that's not helping her. Even given this knowledge, this thing and this thing look uniform, right? So those two things are uniform, even given knowledge of S. This is exactly what we wanted to achieve, and we're quite happy in this toy version. So let's move to the harder variant. By the way, if you have any questions, please feel free to interrupt me. Okay, so let's move to the harder variant. Let's increase the power of Eve. Now, instead of Eve just sitting in the middle and passively listening to the communication, Eve has a power of manipulating the messages. So in this version, Eve has full power over the channel, full control over the channel. It can block the message, it can turn the message in some M1 prime. Then Bob sends M2, Alice will receive some M2 prime, and so on. Eve can do whatever she wants. Okay. In particular, she can do something interesting. She can talk with Bob and not forward any information to Eve. And she can talk with Eve and not forward any information. She can talk with Alice and not forward any information to Bob. So Alice can separate, Eve can separate Alice and Bob, right? There's gonna be nothing going in between them. So we are already in a harder setting. If you notice above, no matter what Eve did, I mean, she was just listening, right? She couldn't interrupt the protocol. The protocol always succeeded and always produced something uniform. In this setting, because Eve has the power to separate things, we can't have a guarantee that the protocol will always succeed. That's just impossible. So already the definition gets slightly harder. Before we could always be successful, now we can't. So what's the security definition? Well, we want that one of four scenarios happen. Either Alice and Bob derive something uniform, equal, and unknown to Alice and unknown to Eve. That's one version. The other version is they both abort. This is a symbol for error, abortion, or yes, interruption of the protocol. So either they both accept have the same uniform output and Eve does not know it, or they both abort. or symmetric case, one of the parties accepts, the other rejects. But again, Eve does not know what this U is. Okay, this is often called post-application security, and it can be reduced to this case and just one extra round. But this idea of Alice and Bob can both abort is because Eve can separate the channels, and they will have no choice but to abort. On the other hand, we obviously want that this happens at the very least if Eve is completely passive. If Eve decides to not do anything, just pass the messages, then our protocol has to succeed, and Alice and Bob has to derive something uniform that's independent. Okay, so this is the standard version of privacy amplification. It was considered by Dodis and Weeks in 2009. And their protocol requires two objects. One of them is non-malleable extractor or non-malleable seeded extractor. What's this object? Similarly as before, it will take something with high mean entropy. It will take S that's uniform. But there's more guarantees. Previously, we had a guarantee that NMX of W and S is uniform even given S. Right now I'm writing back in the column. Right, so previously we just had that extractor was uniform even given S. Now we will have one more thing. You can pick any S prime as long as it's not equal to S, and I will give it to you. And I will give to you the output of extraction with the related different seed S prime. Okay. And this object guarantees that the output of the extractor remains uniform even if I give you the seed S and I give you some output of the extractor on the related different seed. Right, so there's extra power. Okay, I need one more object that's going to be message authentication code. Message authentication code takes a key K and a message and produces tag. And the guarantee is that if you see message M and you see MAC on the message M, but you do not know the key, so you only see this pair, you can't do some M prime and valid MAC on M prime. And in a way, think of it as a signature, except it's only one-time signature. So when you see a message and you see a tag with this message, you can't create a fake different new message M prime and a fitting tag, as long as you don't know the key K. This can be done information theoretically. Think of like polynomial of high enough degree. You can do it degree number of times, right? So knowing some D number of pairs of message and tag does not help you with the D plus first message because just the degree of the polynomial will be high enough. In this case, polynomial will be the key. Okay, so we have those two objects. And okay, let's proceed with the protocol. Protocol starts the same way. We pick uniform S and send it across. Okay. Now, Alice sends S, but what arrives here might be S prime. Okay. Now let's consider a few scenarios. First, if S equals S prime, what happens then? Then X WS and X WS prime is equal, right? Because nothing has changed. Okay. And both are uniform. Both are uniform and unknown to Eve. Okay. So that's first scenario. The second scenario is, what if S is not equal S prime? Then we get that X WS is uniform even S, and sorry, this is NM, and NM X WS prime. Okay, we are in one of those two cases. So let's continue. Now the protocol will go as follows. We already got this and we got this. Now Bob will pick X that's uniformly random. And will send X and mark of X, and as a key, he will use this. Now, Alice will obtain some kind of X prime and mark, or something that pretends to be a mark on X prime. Okay, let's go through the first scenario. Okay, in this scenario, I know that my NMX, so my key that I used to create this mark, matches matches Alice's key, right? So now, if by security of the mark, if anything happened to my X, if X was changed in any way, Alice will immediately detect it because our keys match, right? If our keys match, then we know that you can't forge the message, right? So if S was equal S prime, then we have two scenarios. Either X is equal X prime, or Alice aborts. Okay. And what's the other scenario? Well, if S was not equal S prime, then notice what happens. This is the key that Alice is expecting in the mark, right? I'm expecting that whatever I will get is signed with a correct key. But on this side, Bob does not know the key. Neither Bob or Eve, like both together, Eve, when given access to this thing, will not know the key. So this mark is completely bogus. Moreover, when it's sent across, the knowledge of S is not helping. So Eve cannot create anything that's valid. This message will never be valid. So in this scenario, if S is not equal S prime, Alice will always abort because Mac will not match. Okay, so we are almost done. We managed to get the communication going. And in the end, we know that either we aborted or X is equal X prime. Okay, that's our uniform X. It's equal X prime. Great. So all we have to do is the same thing we just did earlier here, right? The only issue, the issue we had is that when I send seed, it might get changed. But now we have a guarantee that whatever you send, it arrived or you aborted. Okay. So we can finish it by simply applying standard extractor W and S and X. And here too. And we are all happy. Right, so to reiterate, what happened is we ran this whole complicated process just to make sure that what I sent has been delivered, or you figured out that it's something incorrect, right? Once we have that, we can run the standard, the toy version protocol. Okay. So that's the classical privacy amplification scenario. This is a protocol from .NET 09. By the way, it's also the paper that introduces seeded non-malleable extractors. So let's continue. Let's increase the power of Eve even further. So in this scenario, Eve not only has a power over the channel, so she not only can tamper the messages, but she also corrupts one of the memories of the parties. So in this scenario, Alice and Bob share W. A is the random tape of Alice, B is the random tape of Bob. Think of a standard scenario of having a smart card somewhere. Somebody else has a smart card somewhere else, and like the smart cards don't have very huge generation of randomness, so they use some kind of generation from outside, or at least the generation of randomness can be impacted. Moreover, there's some possibility of tampering. So if you run your smart card on the untrusted device, your data might be tampered. So in this scenario, Eve can pick either Alice or Bob. We will decide on Bob in this case, and changes W to some W prime and B to some B prime. So she has control both over random tape and over random input. Okay. What will be the security? The security is we demand that in this scenario, the party that's not corrupted will be able to abort if W was changed. Okay. So that's the security guarantee. In general, if the parties both accept, they will accept the same uniform output. If else, we expect Alice to abort. In this scenario, you can't expect Bob to abort, by the way, because Eve has full control over W and B. So Eve can separate them, can like completely ignore Alice, and just talk with Bob. And since she knows W prime, I mean, she can pretend to be Eve in this scenario. So Bob has no chance of realizing that he's taken for a ride. But Alice will realize that something went wrong, and she will interrupt the protocol. Okay, so let's start. The protocol goes as follows. I take my random coins and I send them across. You get A prime. Now, we can't just repeat the protocol that we did here, right? Because all that strongly behaved, depended on the fact that S is uniform. So this S had to be uniform for the security of this object to work. So, A might not be uniform because Alice might have been corrupted. And then Bob sends B prime. And then, yes, one of those values might not be, either A or B might not be uniform. So we don't have enough power. Right? What we would like to do now is we would like to stick W and A and B into Extractor. Preferably non-malleable. But that creates a problem. Problem is that, first of all, W is high in entropy. Only W is not uniform, clearly. But also this is not going to be uniform, right? So our seeded extractor will not work because seeded extractor required uniform seed. So there's another useful object that we need. It's called two-source non-malleable extractor. 2NMX takes two inputs, X and Y. It's going to be uniform even given one of them. And given one tampering. Previously, we allowed for a seed to be tampered. Now we allow for both sources to be tampered. It's a stronger object. So this object does not require Y to be uniform. Y has to have some mean entropy. X has to have some mean entropy. And the tampering is allowed to be on both sides.
Maciej, I have a question.
Yep.
Yeah, so on the right-hand side, did you mean to write NMX of W prime?
You are, yes.
Okay, and B prime as well, or B stays the same, is it?
No, B stays the same because this is what Bob sees.
Okay.
A prime B. And
Okay.
A B prime is what Alice sees.
Right, but you're tampering Bob's state, right? And Bob's state is W and B, so shouldn't the state itself change to W prime and B prime?
Okay, yes. If we include this, then yes, you are right.
Ah, okay. So then on this side it becomes B double prime. I guess you didn't want that. Is that why you wrote it?
Okay. Yes, that's kind of what I was trying to avoid, but it's not a yes. Thank you for pointing it out. Yes. Okay. So this is what's happening. Now notice that both sides of this extractor have been tampered. W has been tampered to W prime. And this thing has also changed to something related, right? You can think of this as a function that takes this and turns it into something related. Obviously, the condition here is that either X prime is not equal to X or Y prime is not equal to Y. Okay. So now what happens here is I am guaranteed that if something went wrong, if this has changed, or this and this is not equal, I am guaranteed that this thing will be uniform given this. Why? W has high mean entropy. This has some mean entropy because A has some mean entropy, right? B might be fake, but that's fine. And now I know that this is either equal to this if W prime equals W, A equals A prime, B equals B. In other words, if everything went fine, those two things will be equal. Or this is uniform and independent, given this, so given this thing, and A prime B. Okay, cool. So because my security guarantee is like if Bob is tampered, I don't need to provide any security, we can cut this protocol slightly short. We can just compare. I mean, I know that this and this will be equal only if this happened. So what I can do is I can cut it in 3 pieces.
Just one question, Maciej.
Sure.
So why is the second thing? Why is this uniform and independent? So the seed doesn't have entropy, right? A B double prime.
A prime B A B double prime will have entropy because it has entropy from A. This is concatenation, right?
Okay. Two source extract. Fine.
Okay. Yes, precisely.
Okay. Maciej, one more question. So the tampering of B prime into B double prime, so you're not assuming any entropy on that, but it's sort of correlated to W, right?
Yes.
Does that
anything?
change
You have to make it short.
Okay.
In order to reveal it and not kill entropy of W, but that's like technicality. But
okay,
yes,
but that's all you need. Okay.
Yes.
Sounds good.
So you do reveal it just to you do have to reveal B prime because it's a function of joint function of this, right? So this is a small leakage on W. So you have to reveal it in order to maintain split state. Yes.
Got it. Thanks.
Okay, so we know that this and this is going to be equal only in this cool case of everything went smoothly. So all I have to do is cut it in 3 pieces. I will send you the first one. You will send me the second one, and only if we both agree, we will use the third piece as our output. Why do I send you one piece and you send me one piece? Because I don't know if Alice is corrupted or Bob is corrupted, right? If I know that this whole thing is uniform, right? So revealing this part is not going to help. Bob will have no idea what to say to convince me, right? The empty square is independent of the filled square, so Bob cannot guess it, right? So when he tries to convince me, he will fail. On the other hand, if Bob was not corrupted and Alice was corrupted, then Alice has no idea how to convince Bob about field square. Field square is completely uniform from the point of view of Alice. So this is sufficient to get something working. And yeah, we suddenly know that everything went smoothly. The Rust part has to be equal. We are happy, and we finish the protocol. We can continue and get a better efficiency. We can do what we did earlier with what Dodis and Vix did. If you have access to extra randomness, So extra tape A2 and B2. Obviously, B2 will be tampered by Eve. So what can happen is I send A2 along with Mac. This is used as a key. You send B2 with Mac with this as a key. And now I have a guarantee that like my A2 arrived here, because again, the keys will match. B2 arrived here, so I can do something easier and faster than here. I know that A2 and B2 arrived, and I know that at least one of them is uniform and independent of the other. So all I have to do is use standard extractor and A2 and make use of the independence. Now I'm writing W because I know that nothing has changed here. And even if B2 has no entropy, the fact that A2 is independent and uniform is going to solve this problem. Okay. So that kind of concludes this stronger version of privacy amplification with the tamperable memory. So not actually more than tamperable memory, both memory and the coins. But that's not the end of the story. Kind of seems like happy end. Well, not really. Not really, because what we needed is we needed two source extractor that one source is the entropy of W, whatever, it's like rate 0.99%, like high mean entropy rate that we can demand. That's not an issue. The issue is that we wanted to apply it to A concatenated with B prime. Right? We wanted to apply it here. And like, if you look at this source, B double prime might have no entropy at all, right? We just discussed it. So this has entropy rate below half, slightly below half. And that sucks because the best construction we know requires 0.99 in one source and 0.99 in another source. So basically the two source non-malleable extractor that we required does not exist or did not exist until now. How much time do I have?
About 20 minutes.
About 20 minutes. Okay, awesome. I will not go through the whole state of art. I'll omit this one. I'll just focus on two source extractors. So the two source extractor, the non-malleable two source extractor that we require, the best construction by Lee requires 0.99 and 0.99 entropy rate. The right percent here. Sorry. Okay, that's the best known construction. If we do not require non-malleable, this situation is slightly better, but not perfect, actually. For a very long time, we had a problem of we only could build stuff that requires 0.5 entropy in both sources. Then Bourgain had a huge breakthrough that brought it down to 0.499, 0.499. And later on, Levko improved it to 4/9. This is a result based on additive combinatorics, and Levko took the analysis of Bourgain, but included the latest improvements in additive combinatorics. We have RAS extractor that's quite cool and gets polylog entropy in one source, but the other source has to be 0.51. That would be great for us, except this is not non-malleable, so we can't use it. Then there is CZ result dot polylog in both, but has a significant downside from the point of view of this Czetopalej-Zuckerman. This result has a significant downside from the point of view of cryptography because the error it achieves is 1 over poly. There's no negligible error. So the error is the distance to uniformness, right? And 1 over poly is not good enough for crypto. And that's a bottleneck. This construction cannot get better because it's using resilient functions and basically iterating through the whole space. And like the iteration through the whole space will not work if the function is too large. So yeah, we have problem. One problem is here. Those two problems are kind of connected because what we get is improvement here, and slight improvement would imply improvement here in a sense of getting a small mean entropy two-source extractor with negligible error. But I'm digressing too much. Let's just focus on this. So what we do in the recent paper is get two-source non-malleable extractor with one source that requires polylogarithmic entropy and the other source requires 0.81. Like this is already a huge improvement from 0.99 of Lee, and this is even bigger. So yeah, let's go. Yeah, how we achieve this. This is going to be a general compiler. It's going to use two objects. It's going to use E, that's a standard two-source non-malleable extractor, and it's going to use C, that's collision resilient object. I'll define collision resilient object in a second. So our compiler will take one source and the other source. The other source will be cut in two pieces. L will be used here as a seed for this collision resilient object, and repeat it here. Okay. So what's collision resilient object? The definition is like this. We require that C of X and Y is close to uniform and Y. That's a standard definition of extractor. And we require that so X prime is any function of X, hopefully not equal. Then we expect that this is negligible. If you're familiar with leftover hash lemma, what leftover hash lemma says that if you've got such an object with very good probability, a bit more than what we require, but if you've got such object, then it is an extractor. What we showed with Skursky 4 years ago is that if you have an extractor, then it has to have a core that's basically collision resilient. But it did not have to be collision resilient as a whole. So what we require here is, in sense, a model extractor. And a role model for extractors is something that like nicely follows from LHL. We know that LHL, so leftover hash lemma, is the only way to is a way to build extractors. Then there is this result that shows that every extractor has to have a core that fulfills it, and this is kind of a combination of two. We want an object that already has this nice collision resilient property. So what is collision resilient? What is collision resilient? First of all seeded extractors can be compiled at the slight loss of parameters. So you can take any seeded extractor, you can apply a fairly easy compiler that's based on Trevisan extractor. and obtain collision resilient seeded extractor. What else is collision resilient? It's RAS extractor. Again, with small loss in parameters. Okay, so let's compile a few things. What we will be using is we will be using Lie extractor, so two-source non-malleable extractor from Lie. We will be using the seeded extractor by GUV or Trevisan, doesn't matter. Now, what they require, Lie requires 0.99, 0.99. GUV Trevisan requires uniform and polylog. And what we will be building is this source will be uniform, and this source will be polylog. Okay, so let's start analysis really fast. If this is uniform, this is uniform, this is uniform, and this is uniform, that's great. That means that this is uniform and this is uniform. Okay, if this is uniform, we are already fulfilling the one requirement on the Lie extractor. That's great. Now, notice that this fellow is the output of extractor. So this fellow will be uniform, which means it will be fulfilling this as long as we can guarantee that X has some mean entropy. And what mean entropy do we require? We require polylogarithm. Okay, that's the only requirement on X. That's great. We got polylog and uniform. Now, notice that this is significantly stronger than non-malleable seeded extractor because both sources can be tampered. Okay, where the collision resilient object comes into play, collision resilient object comes into play in the following way. We need to guarantee that this thing will be uniform if I change X or I change this. Okay? If I change this, that's great because this changes. And if this changes, then I'm happy because the security of E, so security of two-source extractor kicks in. Okay? This has changed. All great. Security of the extractor guarantees that the output on changed thing will be completely independent. Okay, there's a second case. What if this did not change? Well, if this did not change, this did not change, we have to guarantee that if X is not equal X prime, then something has to change, right? Because if I plug in X prime and I plug in L concatenated with YR, then I require that this is uniform even given this, right? So something has to change, else the thing stays the same, right? So this is exactly where the collision resilience of this object kicks in. The seed has stayed the same, but X has changed. And that's exactly where the collision resilience plays role. Okay, so that's the collision resilience is for the proof of non-malleability to go through.
Maciej, I have a stupid question.
Go
on. So you by collision resistance, you just mean like some sort of a hash function?
Basically, yes, you can append a hash function to it. In case of seeded extractors, yes.
Okay, and why do you need to hash X and Y2? Why can't you hash just X?
Because, I mean, you need a seed for your hash function, right?
Oh, you're using one as the index to the hash function. Okay, okay.
Yes. This is precisely the choice of the hash function. Yes.
Okay, good.
It's slightly more complicated in the other case where when YL is not uniform, you can't just use hash function. That's why it's cool that RAS is hash function even with non-uniform seed. In a sense, you can think of RAS as being hash function with non-uniform choice of hash.
Okay.
Which might be of like independent interest if you need some object like this. Okay, so we already got cool object. One is uniform, the other source is polylog, and we allow for tampering of both sides. Okay, but let's keep on compiling. Let's take this object as E. So we will apply the same compiler twice, and as C we will take ras. So again, what it requires is polylog and uniform. Ras requires polylog and 0.51. Okay, and let's see what we get. Okay. Let's see what we get. First of all, let's look at this. This is great because C is extractor. So this output will be uniform, that will fulfill this requirement. Great. Okay. Now, what's the requirement on X? The requirement on X is here, it has to be polylog. Okay, great. So X, we require only polylog. Cool. And now what's the requirement on Y? Well, on one side here, they need to have some entropy left in them. That's cool. And the other one is YL has to have 0.51 mean entropy in itself. For technical reasons, within the proof, we will have to reveal YL. So the entropy of this is basically only the entropy of like whatever is left in YR. And if you do the calculation, that will require the entropy to be slightly higher than 0.51. It increases to 0.81. Okay, so you get this this super cool object, and that's only thanks to like using non-malleable, like using extractors the way they were meant to be used as a hash function. Yeah, any questions? Obviously, it's a joke, the Jeremy Clarkson. Yeah.
Are there any questions?
I guess I asked mine during the.
Okay, if there are no questions, then we can thank the speaker. Thanks, Maciej.
Thank you. Thanks for having me.
Thanks.
Okay, thank you, Maciej. It was a really nice talk. And I liked all the three